Okay, so this is problem 10 from homework 6 about Kirchhoff's rules and applying them. And we're given this figure here of a circuit with our battery with the positive charge and negative charge. And then we have our flow or our current of electrons going around the circuit. And then 3 resistors, 1, 2, and 3. And for part A and part B, they're talking about Kirchhoff's junction law. And for part A, they want us to describe what the conservation of which quantity does the junction rule describe. That's a weird way to say that. But the junction rule basically is the conservation of charge, because it just says that the current that's coming into the circuit is going to equal the current that's coming out of the circuit. So for part A, it is talking about the conservation of charge for the junction rule. And then for part B, they want us to apply the junction rule to the junction labeled with number 1. So this junction right here. So to apply our junction rule, we know that the sum of our currents, the total sum of our currents is going to be equal to 0 because the flow in is equal to the flow out. So we just need to take the flow into the junction, which is going to be current 2 and current 3 flowing into the junction, and subtract the junction coming out. So we're subtracting current 1. So I kind of did this weird, but I'm taking current 1 and then I'm subtracting the current 2 and current 3. But I could also put current 2 plus current 3 minus current 1. But yeah, just basically currents 1 and 3 are going into it and 1 is coming out. So our answer is just current 1 minus current 2 minus current 3 equal to 0 for part B. And then for part C, they want us to apply the loop rule to loop 2, which is this smaller loop here, and sum the voltage charges across each circuit element around the loop going in the direction of the arrow. So notice the arrow is going counterclockwise. And then for Kirchhoff's loop law, it basically just states that the sum of all the potential differences encountered while moving around a loop in a closed path is going to be equal to 0. So if we're just talking about this loop 2, the only potential differences we're encountering here is from the first resistor and the second resistor. So remember from Ohm's law, we know that the potential difference is equal to just the current times the resistance. So if we apply this to that first loop, we just take and because we're going in a counterclockwise direction, we're going to take our first potential difference, which is going to be equal to the current 2 times resistance 2, because we're just looking at this first loop. So we take this first potential difference we encounter, and then we're going to subtract that second potential difference that we're encountering. So we just take current 2 times resistance 2 and subtract current 3 times resistance 3. And that will give us the sum of all of our potential differences around that loop. So we know that the sum is equal to that first potential difference of 2 minus the potential difference of the 3, and that's going to be equal to 0. And then finally for part D, they want us to now apply the loop rule to loop 1, so the larger loop, spanning the entire circuit. And same concept there. So this one's moving in a clockwise direction. So for this one we need to remember we have our potential difference of the battery here. So we need to take that battery, which is going in, and we need to subtract our potential differences coming out. So we're just going to take our voltage of the battery minus that first voltage or potential difference, same thing that we encounter, and then minus the second one that we encounter. And then, yeah, we get the V of the battery equal to V1 minus V3, which is equal to 0. And yeah, that all ties into what we're learning in chapter 27 with circuits and currents and resistance, and yeah.